This conference will now be recorded.
Okay, so this is the assumption we are making. We are going to focus only on function that take a pre-built tree as input, and then we will go about solving the problems. So I'll introduce you some code so that we are able to visualize the tree, we are able to see things. So if I talk about BST input format, first line will be number of test cases. Line 1 will be T, which is, let's call it number of test cases. Then each test case has, there is again some disturbance from someone. Yeah. So each test case has 2 lines of input. First line will be line 1 of test, or let me call it test case line 1. It will be n number of nodes in the tree, and TC line 2 will be n space separated numbers, and I'll call these numbers are distinct, no duplicates. Just to keep things simple, we are going with this, right? So if this is the input format, let's try to have some input with us so that we can ideally form a tree, and we can keep that in mind whenever we are solving any coding problems. Yeah, so let's build a binary search tree. So if root has 13, let's put 9 here, 5 here, 12 here, let's say 11 here. Then 13 can have 23. Left side, let's put 19. Here, let's put 44. Any random thing I'm just putting, and let's put in before 44. Let's give it 39. Yeah. So this is our BST that is kind of one input. Let me put 56 here. Yeah. So for this BST, can I say the sample input that we have will look something like one test case, 13, 923, 923. Then we have 5, 12, 1944, 5, 12, 1944. And then we have 11, 39, 56, 11, 39, and 56. And total number of nodes we have to put just before this, 1, 2, 3, 3, 4, 7, 3, 10. So we have a 10 node tree. So this is clear to everyone that this is an assumption that we are going to take. The tree will be built and given to us. Now you may ask, like, how will we get the tree? So I have some pre-written code that we are going to use. So code CPP, we go with code bean03 BST template. So this template has a few advantages. In this, I have put up code that can print our tree also. So we can visualize the tree directly. So ideally, if you go directly to the things that you have to pay attention to, we need to pay attention to the struct that we are declaring. So our structure is going to be this. Then our main function is going to be in line with whatever input we have passed. So if you see, okay, Gopi, there is disturbance from your side. Yeah, so if you see, we are reading T, then while T minus minus, we are reading N, we are declaring a root inside the while loop, and we are reading a number X, we are doing insertion. So insert function and create BST node functions. These are the critical functions that we will be using. So this, if you go and take a look, we have declared the tree node structure, and then we have created a function to create one node, and then we are doing insertion. Now with this, I believe like our main function that we have, ideally let's simplify main function also. So in T, let's make it C++ version, C in T, while T minus minus, let's call it C in M. Then BST node star root, for loop, C next, and then we are running. Okay, so then there is a function here. I have pretty print. This is a little longer code, but we will see what benefit this provides to us. I have not declared n, so let me declare n here. I have not declared x, let me declare x here. I is not declared, so let me put I here. So now I believe this should be good. G++ being 0, BST. G++ being 0, BST template. Let's compile this. String length was not declared. Okay, so for string length, we will need to include string.h. Okay, now we see this code is compiling. Now, if you ask me, like, if we run this code with the input that we have envisioned, with this tree that we have assumed that we are going to use, let me take this snag or snip for this. So this is the tree we are using. I'm putting this also in this doc that we have. So this is the tree we are going to focus on. Okay, not enough space to fit here. Okay, so this is thing we are proceeding with. Now input that we have, let me copy this input from here. And if I run this code a.exe now, and if I paste the input, you see this code is printing a tree also, right? And this is the tree that we had drawn. Just compare it with this. 13 has 2 children, and then 5, 12, 11, 9, 23, 44, 39, 56. Yeah. So this code has some code for printing the tree, which will help us visualize any tree. Tomorrow, if we change the input to any other tree, we will be able to visualize that also. And okay, I think here it is not coming properly, so let me get rid of this. Okay, so we are going to leverage this code, and whatever coding problems we are solving, we will solve using this. So that means if we are doing any of these problems, we will be focusing on just writing that function, because main function is anyways building a tree. Here, if you see, we'll assume if main function has built the tree, then all we have to do is we just have to comment out pretty print, and we will write our function over here, and we will get going. So fundamentals wise, I hope we are clear that what we are going to work on. Let me bring main here. This main is pretty print is not there, but rest of the code we can visualize, we can see here. And I want to make sure that this code that I'm sharing with you, if you guys want pretty print also, I can share this entire skeleton with you. But in this Word doc, I'm just putting whatever is necessary. Pretty print wise, I'll put that in ID1 and share that separately. Yeah, so this one, I'm just trying to make sure that this one that I'm sharing with you, it is compilable. So let's see, basic BST template.cpp. So G++ basic BST template. Okay, there are issues. Scene was not declared. Okay, we missed using namespace std. That is it. Yeah, so now we have a compilable code. Let me bring that into our share. Okay. So now let's look at these questions that were raised by Kushal. So first thing that we all should know and we all should understand is how to do level order traversal. These are the prerequisites that we all should know. One, we should know how to write a recursive in order, pre-order, post-order traversal. This I believe everyone is comfortable. If somebody is not comfortable, can you type in the chat window? because without this, rest of the class will not make sense. I assume then everybody is comfortable. Level order traversal. Everybody is comfortable with level order. Anybody who is not comfortable with level order traversal? Because we are going to use these things when we are solving the problems. Okay, so I assume here also people are comfortable. Third thing I will say is recursive thought process about trees. This I will talk briefly, and I'll not assume that everyone has this clear. So, but if you are not comfortable with any of these, then rest of the class is going to be a little challenging for you. If you are clear with these, then things will make much more sense with whatever we are discussing. Apart from that, we should be clear with STL, Q, and map. They are essential. That people should know how to use map and how to use Q of built-in STL. I'm hearing some disturbance that is from Dikshit's side. Dikshit, can you mute yourself? Yeah, thanks. Okay, so let me talk about what is this recursive thought process that we are saying that should be prerequisite. Now in tree, typically if you see, information can flow from children to parent or parent to children. There are two ways we can solve the problems. Many problems are solvable with both the ways. So that information flow we should be able to visualize. So if we take one example here, let's say we want an example. Example for third prerequisite is find maximum sum from root to leaf. If this is the problem we are trying to solve, let's go back to our tree that we are envisioning. What is the maximum sum? Oh, ideally this is a BST. So in BST we know maximum sum will always be on the right side because it is always increasing. Would we have any example where maximum sum can be on this side also? Ideally we know maximum values will always be on the right side. But would we have any example where maximum sum can be this path? Is that a possibility? So ideally, if we have a tree like, yeah, skewed tree, obviously. If we have a tree like 12, 11, 10, even if it is not a skewed tree, even if there are values here, imagine there is 13 here, then there is not 13, let me put 14, there is 13, and there is 15. I can put more nodes to the left side. After 9, I can have 8. Now, can I say this sum is actually bigger than this sum? And because this is 26, yeah. So this kind of tree we can have. So ideally, let's say we are solving this problem where we are trying to find the maximum sum possible in the tree, and we can consider all the paths from root to leaf. Now, we can think of solving this problem with multiple approaches. Let's see approach 1. Approach 1, we will say that root will give us the answer. That means we are giving the responsibility of answering to the parent, and in order to give the answer, parent can take help of their children. That is the first approach we will talk about. And here, this thing that I'm talking about, recursive thought processes, parent to child communication and child to parent communication. Those are the strategies. Parent to child and children to parent. These are the two strategies we will take. So when we say root will answer, so look at this tree. Here we are asking 13. 13, you need to tell us what is the maximum sum possible from U to any leaf. So what can 13 do? 13 will ask its left child, you tell me maximum sum possible from U to every leaf. It will ask right child, you tell me the maximum sum possible from U to leaf. And whatever answer these two children of 13 give, 13 can take the max of those two and add himself and say, that is my answer. So for example, if we see, 13 will ask that question to 9. Let's see what 9 will do, because here communication is happening from parent to child. And when we are going from parent to child, children have to calculate the answer and help the parent calculate the answer. So 13 goes to 9, 9 goes to 5. 5 knows that it is a leaf. So 5 does not have to ask anybody. What answer can 5 give back to 9? What is the maximum sum possible from 5 to any leaf? Can I say it is 5 because 5 is a leaf node? 5 will say to 9 that my answer is actually 5. Okay, let me get the old tree back so that we can draw and discuss area. So here we had 56. So see, what we are talking about here is 13 needs to give us the answer. In order to get the answer, we are saying 13, you only tell us the answer. Whatever you need to do, you go and talk to your children. 13 goes to 9, 9 goes to 5. 5 is the base case. 5 will say, hey, my answer is 5. The answer we are asking is, what is the maximum sum possible from you to leave? That is the answer 5 gave to 9. Now 9 will ask 12 also the same question. 12 will ask 11 the same question. 11 can give the answer. My answer is 11. Same way, 39 will give that answer. My answer is 39. 56 will give answer. My answer is 56. 19 is a leaf. It will tell that 19 is my answer. Now let's see. In 9, both the children of 9 have given the answer. Sorry, 12 will give the answer. What answer will 12 give to 9? Because 12 got an answer. 11 says, from me to leaf, answer is 11. Now, what is the answer from 12 to leaf? Can I say 12 will take this answer, add himself? 12 will tell 9 that from me to leaf, the answer is 23, right? So 9 got two answers. 9 says my left child is saying 5, my right child is saying 23. What will be the 9 answers to? What will be the 9's answer to? Its parent, 13. Yeah, it will be 32, because what 9 will do, 9 will select max of these two and add himself and then give the answer, right? So what we are doing, strategy wise, we are saying that here our approach is function wise, it will be int max path sum from node to leaf. I'm not putting root, I'm putting node to leaf. BST node star root. Now we have to give the max answer here. So what we discussed is, we said first get answer from left child. That is what R will do. Then we will say get answer from right child, and then we will say return. What answer should we return? R arrow. What was our node structure? It was data is a field name, so we will say R arrow data plus, because we have to add current data anyways. We said 9 will return an answer, 9 plus max of the answer coming from its children. So can I say this plus max of left answer, comma, right answer? Is this making sense? That parent is asking children, that is, it is making recursive call to children. Children are finding the answers, and that answer it is returning. Parent is returning based on the answer it got from left and right. So this is recursive thought process where parent is taking help from children. So parent is asking children. So it is ideally children to parent communication, because children are returning the answer to parent, and this communication happens when child has to send something back to the parent. Return value is the way of their communication. If you see, this return type is int, that means children are going to give that return type to the parent. Now if we have to think about what will be the base case here, who will not ask, who will not make recursive? So what should we use as base case here? Leaf node, yes. So we can say if R is leaf node, what should we return in that case? If R is a leaf node, what does it return to its parent? Chakradhar says 0. Chakradhar, think about it. It will not be 0. 5 is a leaf node. What should 5 return back to 9? It should return its own data, right? Yeah. So ideally, we will say that if R is a leaf node, we will be returning that node's data back to the parent. So we can say return R arrow data. So this is what is going back to the parent. So parent will get to hear this data. Now one more case we will say that is a boundary case that we need to keep, and that boundary will be if R is null, then what should we do? In such case, what should we return back to the parent? Because we can have a border case also, boundary case also. Yeah, absolutely. We should be returning 0 to the parent, because if tree is an empty tree, we know the answer is 0. There's no sum possible. Right? Now, if we convert all these things into code, let's see that. So here we will go and say int max sum path, and we will say BST node star root. Now we'll say if R is null, so I can put if not R, it's a shorthand way. We can say return 0. If R is not null and it is a leaf, what is the check for leaf? If R arrow left is null and R arrow right is null, in that case we will be returning R arrow data. Otherwise, we will be returning R arrow data plus, we said max of, we'll make the function call, same function call, that let's find max sum path R arrow left, comma, max sum path R arrow right. So we are making two function calls, and whatever is the max of those two, that is what we are returning. So this is the function. Now we will call this function for our test case, and we'll see, is it giving us the desired output? So let's do cout, put this and make it root and make it /n. So our input is pretty clear to us. In this, can you tell what will be the max answer that we are expecting? What is the sample answer that we are expecting for our tree, so that we can validate whether our code is giving the correct answer or not? So what is the max sum path in this tree? Can I say it will be this only? Let's use your mathematical skills quickly. Can you give me this sum? Yeah, so Bharadwaj says it will be 136. Sure. So let's go ahead with this, Bharadwaj. So we'll go with this and see whether we get the sum 136 or not. So we'll do G++ and what file I'm updating basic BST template only. So G++ basic BST template. So we compiled the code. Now let's run the code a.exe, and our sample input we had pasted in our shared node. So this shared node has our sample input, which is this. So let me copy this once again. To make it convenient, I'll just store it in a file, basic bst template.inp. So I have stored it in a file so that I can directly give that input, basic bst template.input. Yeah, so let's see. So we are getting answer as 136. So that is the correct answer that we are getting, right? And if you go back and see, this was the code. Now, I think in chat window, somebody commented, let me go back to that. So Shravan was saying that we should return int min in such case. Shravan, think about it. Should we return int min? If the tree is empty, I think it will give wrong answer. Isn't it, Shravan? In DP kind of problems, yeah, we do require. Yeah, we are coming to your point also, Sushmita. That's a good observation. And good that you noted it. So Shravan, you are clear, like here returning int min will not be a good idea, because if we have empty tree, the answer is actually 0. It's not int min. Second thing, if we have a tree with one node, which is 15, I think that we are taking care already here. In DP kind of problems, yes, we do return that from int min from border cases. Now, Sushmita is saying one thing. Sushmita says, even if we do not have this case, this code will still work. Do you agree with her? She says we don't need, this is a redundant code right now. Yes, why? Because if you have, let's say, a tree which is only 13, and let's say this has 0 here, not 0, let me put 5 here. Now, if we are doing the calculation, 13 will go to 5 because now we have removed this case. 5 will also make a left call because even though 5 is a leaf, it will make a call with null because left is null. It will make a call with right, which is null. So when we are making call with left, which is null, right, which is null, in that case, we are returning 0. So left will return 0, right will return 0. Max of these two is anyway 0. 5 will be returning 5 plus max of these two, which is 0. So 5 is returning 5. 13 will return 13 plus 5. The answer it gets from the child. So this will work, right? So in this case, if you see, this case is actually redundant. If we are removing this case, we are just making two additional calls because leaf node will also make left and right call and it will work. So this is first understanding because this thing we will apply when parent has to answer and children help the parent calculate the answer. So here we always rely on the return value. So here decision maker is parent is decision maker. And children are basically helping the parent in make the decision, and return value is what we are relying on. Second approach that we talk about here is approach 2. Children are decision maker and parent helps children, and we say parent helps children. And how can parent help child? It is by passing input parameters. We will see what that second approach is so that we can understand it both ways. Now let's change our strategy. Here, previous case parent was answerable. Now parent is not answerable. We say 13 will not answer, but what 13 will do, 13 will say, let leaves decide what the maximum sum is. I'm not going to decide. When we come to 9, 9 wants to know from the parent, like how much was the sum up to you? Because below me I can calculate, but up above me, parent has to tell. So this time, if you see what change we are doing is 13 will tell 9 that before you sum is 13. Now 13 is passing itself. 13 is telling 23 also before you sum is 13. Now what will 9 pass to 5? What is the sum? That 5 should know what all is the parent sum. If you start from root, come to the leaf, 5 should know what is the sum above me so that 5 can calculate the answer. So what should 9 pass to 5? What sum is before 9? Sorry, what sum is before 5 in parent chain? It is 22, right? So 5 needs to know from its ancestors, from the parent and then this parent. 9 should tell 5, hey, 5, sum before you is 22. Now you can decide. Now when we come to 5, 5 gets to know 22 before me, I am 5. Then sum up to me is actually 27. So let's do that. So this is 13. This is passing 22. And 5 gets to know 22 plus 5. My answer, if you were to ask my answer is 27. That is what 5 knows. So, but can 5 make a decision that this is maximum or not? That answer is no. 5 cannot make that decision. 5 has to give opportunity to other leaf nodes also, because here leaf nodes only get to know what is the sum till that. So 9 will pass 22 here, 12 will pass 34 here. Now this guy gets to know that sum here is 45. That is what is the answer of 11. Now same way, these two leaves got to know their answers. Let's look at the other leaves. 13 will tell 13 is the sum. This guy will tell 46 is before 36 is before you. This guy will say, okay, 36 plus 19, 55 is my answer. Same way, 13 plus 23 will pass 36 here. So here parents are passing the sum value so that children can make the decision. And each child's answer we know, we will store it in a global variable so that we can update the global strategy we are talking about. So let's come back to this. We maintain a global variable that will get max answer. Each leaf has a responsibility to update global variable if the leaf yields better answer or higher answer. So this is what we are going to follow. So now if you ask me what will the function signature look like, this was our approach 1. Let me make it 1, make it 1 here also, make it 1 here also. It was parent was making the decision, and now since child is making decision, I'll say int max sum path. I'll make this function bst node star r, and let's write this. Now we said parent will pass something to the child also, but this function does not take any additional parameter. In such cases, we will make a separate function, and let me typically we call such function as helper. Why we are introducing a new helper? Because we want to add additional parameter, and I'll call it sum so far. What is the sum that we got so far that we are passing to this root? We will be calling this function. We will take a global variable also, max answer. Now this function's responsibility is to initialize max answer with int min. So we are first putting a minimum value, or you can also say let's put 0, because here 0 is important. If tree is null, we can return that answer. Now we will make a call to helper, and now pay attention that this helper is not returning any answer. Answer will be known by leaf. Leaf will update the global variable. Here we have changed the return type to void. Now we are passing root here, and sum so far that we should pass. What should be the sum that we should pass to root? Can I say it should be 0? 0 is the sum so far, and in the end we should return max answer. Right now let's see what we are doing here. Whenever we are coming to r, if r is null, that means we have reached a null node. What we should do, we should say if sum so far is bigger than max answer, we should update max answer. So shorthand way, I will write max answer is equal to max of sum so far comma max answer. This is a shorthand way of writing if sum so far is greater than max answer, then update max answer as sum so far. So rather than writing these two lines, I prefer using the max function, which is built in C++ in algorithm. Let me put #include algorithm also, that is C++ file, so that we can use that function. You may ask why I'm not putting bit/stdc++.h. Typically I use Mac as well as Windows. So in Mac that bits file doesn't work. So that's why I prefer including individual header files so that my code can work in both the machines. Okay, so this is, we are updating, and once we have reached the leaf node, we will simply return. So this is ideally, if you see, this is not the leaf node. This is actually below the leaf that we are making a decision. Now, otherwise, what we are doing, if we have made a call to root, what call will root make to left child? Call left and call right. Can you tell me what call should I make? Look at our approach. In approach, we were saying root will pass something to the left, pass something to the right. So what call we should make? Max path helper. Yeah, what should be the first parameter? Okay, Sahit is saying we should pass our left and we should pass our data. Is that correct? There is something wrong here that we need to kind of fix. We will not pass our data. That will be true for root. Root is passing 13 to left, 13 to right. But 9 is not passing 9 to 5. 9 is passing 22. Right? So we need to include sum so far also, yes. So current data and whatever sum we got from the parent, that we will be adding and passing, plus sum so far. So these two things will make up the answer. So now if you see, we are going to use our second function that we have written, and I'm calling this function only. Previous function I have renamed it to maximum path 1, so we will not call that function. Let's run this code now, compile, and we go and run this code, and we see answer again we get as 136. So both the approaches are giving us the same answer, and you would have seen like what child to parent communication looks like, what parent to child communication looks like. That is what was the prerequisite that I was talking about, that we all should be comfortable with. And let me include this code also as part of our template code that we have discussed. So both the approaches are there. So this is something, this is important because they help us solve tree problems with ease, because we will be able to see which direction we are moving, what information we are passing. I see some code is sent here in the chat window by Bharatwaj. So max of fun. Sir, can't the tree have negative values? Yes, tree can have negative values also. Good question. Will our code work for negative values or not? The way we have written the code, let's see if you have raised the doubt. So you are asking, Bharatwaj, you are asking this on first approach or second approach? Second. Let's see. In second approach, what we are doing, even if tree has negative values, let's take one example. Here there is -5, -7, and -3. This is a valid BST. Now, what is the max sum possible here? So max sum, can I say it is -8? This is the maximum possible sum because -8 will be greater than -12. So -5 will make a call to -7. -7 will make a call to left. It will make a call to right. So when -5 is calling this, -5 got sum so far as 0 because that is what we are passing to root. What will -5 pass to -7? It will pass -5. What will -7 pass to its left child? It will pass -12. It will pass same to right also. So these two null nodes get to know that their answer is -12. Now the thing is, we were updating our answer, max answer, as max of sum so far and max of answer. Okay, what you are saying is right. Since we are initializing it with 0, 0 will be better or bigger than -12. We are comparing max, we have initialized with 0 and this with -12. So here we will be saying that our answer is actually 0, not -12. So there is a bug here. Yeah, so how do we fix that is, can I say we'll initialize with int underscore min. That should be the default value. And here we can directly say if root is null, handle that case separately. If root is null, our answer should be 0. Otherwise, we should return whatever is the calculation coming from. Yeah, that is a good catch as well. So this will be fine. Yeah, so now if we give this input -5, -7, -3, then we'll take care of those cases also. So let me include this in our class notes that we have put here. And that was the second function. Yeah. Okay, so now we understood the basics, the prerequisites. Now we are good to actually move ahead to the problems that were the focus for today. Yeah. So the first problem that we are going to talk about is left view of the tree. So given a tree, we want to print the left view. What do we mean by the left view? That is, we again lost the tree. Yeah, this was our tree. So left view means if you are looking at the tree from the left side, you should be printing only those nodes that are visible from the left side. So here you are viewing the tree from, your eye is this side. And if you are seeing the tree, what should be the output for left view of this tree? You can see 13, you can see 9, but 9 is before 23. So 23 will be hidden behind the 9 if you are seeing the tree from this side. So 9 will be printed. Here 5 will be printed. Here 11 will be printed. And imagine if 39 had one more value, which is 25, even 25 would have been visible from the left side. So left view of the tree for this tree will be 13, 9, 5, 11. Ideally, that was not earlier in our input. So we can say output should be 13, 9, 5, 11. If we include this, we'll say 25 also. So what should be our strategy for printing the left view of the tree? Yeah, society says it should be the first element of each level. So level by level, if you go, it is actually every level's first node you have to print. So it is just a modified level order traversal that we need to do. So Kushal, you raised this question. Do you feel comfortable coding this? It is a modified level order traversal. You should just be aware when the level is changing. And for each level, you have to make sure you are printing the first node of that level. Kushal, you're there? Yeah, sure. You can try, because these problems are just modified form of that. If still you don't get it, just use our WhatsApp group. You can share your code, seek help over there. But yeah, these 5 questions that you have sent, they have similar strategy that we will talk about how to solve these categories of problems. So this is, I'll help you with one thing, that if you want to do a level order traversal, in fact, it will not be direct level order that we will talk about. I'll say do level order traversal of this tree in such a way that output should be each level on a separate line. So what I mean by that is your output should be 13 on first line, 923 on second line, 5, 12, 19, 44 on third line, and this on fourth line. So what we are saying is we have to print each level on a separate line. Okay, who is this bad rabbit in the chat window? Can we use indices? If we move, decrease that value. Yeah, Harshvardhan, we are coming to vertical order also. That is also part of our plan. So we will talk about these 5 questions that, oh, there is no vertical. Yeah, there is vertical order also in the plan. We will talk about all these 5, how we should think, how should we do. I'll share these practice problems also in HackerRank. You can give it a try. And after that, if you struggle, if you don't get it, then we will discuss their solutions also. But today's class is more of the approach we should take to solve these categories of problems so that we feel comfortable. Does that make sense, Harshvardhan? Yeah. So whatever strategy you have in mind, you can apply that. So I see, I don't know the name of this person. He has put his name as Bad Rabbit, but that's fine. Can we use indices to move right and increase the indices value? If moving left, decrease the value. Yes, you can do that. You can give it a try, how you are actually doing. Strategy wise, we have discussed. For every level, you are printing the first node at that level. How you figured out it is the first node of that level, you can have various strategies to implement it. You can have multiple solutions actually to solve this problem. Yes, start from root with 0 index, then go left, then go right. Yes, you can do that. Okay, Bad Rabbit is Zakiuddin. Thanks, Raghuvaran. Okay, yeah, Zaki, you can try with your approach. And ideally, I will say you should have multiple approaches to solve these problems, because they develop your habit, or they develop your thought process to deal with recursion with trees. So we will treat these as kind of good exercise. I'll share the link also where you can solve those problems. So do give it a try, so that these all 5 problems everyone should code. And if you have already done them, then I think, yeah, today's class is just a quick revision for you guys, but it is not something that where you are learning anything new. So left view is something that we discussed first. And let me make it. Yeah. 1, 2, 3, then 4, then 5. Yeah. So one more thing that if we have to talk about, that I was saying, we'll talk about level order traversal. How do we do? So I'll do level order. So level order traversal typically is done using queue. So I'll take a queue over here and I'll call level order R. So if root is null, then we will simply return. There's no level order for that. Otherwise, we will take a queue. It's like BFS in graph. In queue, we are storing every node's address and we take a queue. In queue, we will do a push. We'll add root. Then we say while queue is not empty, not queue not empty. We'll say take the element out of the queue. So I can simply say queue dot first or queue dot front is the function. So we are printing that front element. Then we say queue dot pop. We are removing that from the queue. Now the thing is, in queue we stored BST node star. So I can directly say queue dot front because this is the address. When I'm printing the data, I'll have to print R arrow data. I'm reusing the variable R. I could have declared a new variable here, but I'm using front, put in R data we are printing, we are removing. Now, if left child is there, if R dot left is not null, we'll put that in the queue. And if R right is there, we'll put that also in the queue. And eventually, this will make sure queue gets empty at some time, some point, and we complete this function. So let's go back, compile the code. Queue, I think we have to include #include queue. And level order R was not declared. There is in main function, I'm using root as a variable, so I should be passing root. Here, this is not R. Here we have put it R. So let's compile a.exe and basic BST template input. So now if we see, right now we are getting level order traversal for our tree, which is 13, 9, 23, 5, 12, 19, 44, 11, 39, 56. So that is the level order traversal. Now what I said is we want to make some change. We want to make change in such a way that each level should be printed on a separate line. How do we make that happen? So somehow we need a level marker that one level has got over. So there are two strategies to kind of deal with this, that how do we mark. So Sahiti says queue size. Sahiti, will that work? Imagine if I give you a tree like this, 13 has a left child 11, it has a right child 12, 12 has, okay, 12 will not have any left child here. So let's say this is 19, this is 13, and this is 12. Will queue size give you an indication? Because now this is a valid BST. Ideally, you are assuming first is one node, second level, two node, third level, four nodes, then 8 nodes. Is that correct? Queue size will not give you the hint. Right, Sahiti? Or you have any other approach? Yeah. For every node, we can attach level. There are two strategies. One strategy, simple strategy we will talk about is we want level end marking. So what I can do, I can also start putting null in the queue. The strategy wise, if you see what I'm doing is, I'll take a queue and I'll say, let's put 13 and let's put null also. The meaning of null is, because we are storing pointer, the address of 13 and null we can put. Now, whenever we get null, we will get to know that level got over. So take 13 out, print 13. When null comes out, what will you do? You will say, okay, null is out, first level got over. When 13 comes out, you will print 13, you will push its children 9 and 23 in the queue. And then you will move to null. When null comes out, you will put a new line and you will say, let me put another null here. Right? So that will give you the level, that it will give you the indication that your level got over. So I'm putting null, and reason we are putting this is end of level marker. Now when we are taking this out, we have to handle, if R is null, we have to do something else. Whatever earlier we were doing, that will continue. So this is something that we need to do. And we have to make sure every time we are taking R out, we are removing that from the queue. Now, because we are putting null also, if null comes out, its handling will be different. When null comes out, we want to print a new line, that is to change the level. And we should also put null in the queue. Because if first level got over, it would have pushed all its children also in the queue. And we should also put a null back in the queue. So let's see what strategy is this and how this is going to work for us. So let's go back to our tree and pay attention to this. So, and visualize like what is going to happen now. So we are taking a queue now where queue has a null in it, and let's see what it does. So this is our queue. First we come to root, we put 13 and we put null in the queue. That is what we have. Now we start the while loop. While queue is not empty, do something. So when 13 comes out, we'll go to the else part. When 13 comes out, root is not null. So we come to this else part. We are first printing 13. So 13 will get printed on the output. So this is our output. 13 is there on the output. Let me put output in green. After 13 is printed on the output, we'll put its children to the queue. So children of 13 are 9 and 23. They are not null, so we put them in the queue. So 13 is done. It has done its job. It is out of the queue because the moment we take it out, we print it, we put its children. So that is removed from the queue. Now we go to null. When we got a null, what are we doing? When we get a null, we are printing new line and we are pushing another null. If you see, null is removed, new line is printed, and another null is pushed. What is the purpose of this null? This null is saying 13 was at level 0, it has put all its children inside. Now when first level got over, it means all the children of second level are already in. Let's mark the end of second level. So this is the state we are in. And let me print this output somewhere here so that we get some space for printing out. So 13 and a new line is done, and queue state is these three values are there in the queue. Now next we take 9 out from the queue, we print 9, 9 will go in the next line. 9 has both left and right children, so 9 will put 5 and 12 in the queue, and 9's job is done. Now we take 23 out. When we take 23 out, 23 will be printed after 9, same line. Then 23 will put its children. So 23 has 19 and 44 as children. So we put 19 and 44. That is there in the queue. Now, next after 23, we get null in the queue. So null is there. So null will put another new line and null will put n here. So now the queue looks like 5, 12, 19, 44. That means this level is already in the queue. That is what we see, and n we are putting so that we mark the end of next level. Now same thing will happen. 5 will come out. 5 will print himself, and there is no children of 5, so 5 will not put anything in the queue. 12 will come out. 12 will print himself. 12 has one child, 11. 11 will come after null that we are putting. Now 12 is gone. Now 19 comes out. 19 prints here itself. No new line. Then 44 prints in this line itself. So all these values are printed in this line. After 44 will put two more children in the queue, 39 and 56. So queue has 11, 39, 56 in the queue. Now we have gotten null. When null comes, we get new line. And after new line, we put null in the queue once again. So if you see the current state of queue, if I redraw it, it is 11, 39, 56 and null. That is what we got in the queue. That is what is remaining in the queue. These values are there. Their end of level is also marked. Now we'll take 11 out. 11 doesn't have any children, so 11 will print. No children added in the queue. 39 comes out, prints. No children added to the queue. 56 comes out, prints, and no children added. Now null comes out. We do a new line. We put another null. Now this null comes out. We print line, another null. So this will become an infinite loop right now because whenever a null comes out, we are putting another null. This will always get into infinite loop. So here we have to be cautious. If a null has come out, and after null, if queue has become empty, we'll break. See what we are doing. to avoid this situation, when this last null came out, we removed last null, we put a new line here. After that, we are going to insert a new null. That is what we are avoiding. We are saying if after taking this null out, if Q has become empty, break your loop. Don't go further. This is to avoid infinite loop. So this is something that we can go compile again. And let's run this. And we see that we are getting output of each level on a separate line. So this is something that this is one way of achieving things, that every level you know when it is starting. Now you can easily modify this code to print the first node of that level or last node of that level. The left view is easy, and this is one approach. Second approach that Kaushik was mentioning, I'll let you guys work on that. In queue, do not put only VST node. In fact, in queue, put the node as well as its level. So strategy wise, if you ask, what is it that we are talking about? So you take a queue. In queue, you are putting a pair. Two things you are putting in the queue. So what will actually go in the queue? You will not put null. You will put for 13, you will put 13 and 0. You are saying level of 13 is 0. Now when 13 comes out, you will say put 9 and its level is 1 because parent level is 0. So child level is 1. For 23, you will say 23, its level is 1. So with each node, you are storing its level. Whenever level changes, you will get to know that we are on a different level. Current level is this, next level is this. Based on that, you can print new lines. Right, so that is second strategy where you are storing levels along with the data. So I'll just put the thing here. You will take a queue of pair of BST node star, comma, int. So this will be the queue for the second strategy that we are talking about. In place of queue, you can also store their answers in a map, but no, I think we'll go ahead with the queue because it is, we have to go level by level. So Kaushik, this is what you were specifying as a strategy. Yeah. So ideally, there are multiple implementations possible. It is not necessary you have to take a queue of pair. You can still manage with this queue, but for levels, you will have to use a separate data structure. You can also take a queue and a map, but let's not go there. But try this solution with both the approaches, with putting nulls, because sometimes in interview, interviewers may ask you, what if I do not allow you to put nulls in the queue? How will you solve this problem? So you should have another alternate way of doing this. Okay, so left view should be clear now. Okay, Bharadwaj say take queues. Yeah, Bharadwaj, you can manage with 2 queues also and solve this problem. Yeah, you should, ideally the thing is you should be able to think of an alternative when interviewer starts putting restrictions on you, when he says like, what if I don't allow you to do this? So that is where you need to come up with a different strategy. Okay, Shravan has a question, sir. Without taking a queue, only by taking level and pursuing according to level? Yes, you can do that also. So yeah, Shravan, there is a recursive approach also that you can follow. Yes. So in recursive approach, again, parent will pass some information to its children. I am at level 0, you are at level 1. This guy will say you are at level 2. That is where you are saying parent to child communication. Yes, you can do this code recursive also. Yeah, in fact, I'll put that in our notes, that this problem that we talked about, level order traversal, print each level on a separate line. First solution, code it with queue with null inserted. This is iterative approach. Second approach is also iterative, where you are keep track of level of parent and children, which is again an iterative approach. Now you take one queue, you take a queue and a map, That is again a implementation. Approach 3 is a recursive approach where parent passes level to children. Ideally, try all 3 approaches so that you feel comfortable with this. Yeah, probably once you have tried all these questions, I can share the solutions also of all the approaches. But first is, are you able to think yourself? Are you able to code yourself? That is what your first aim should be, right? Can I say once we are able to solve this level order problem, we will be able to easily do left view and right view of the tree, because left view is first node of every level is the left view. Last node of every level is the right view of the tree. Right? So now how do you figure out last node is up to you. So you can try your approaches. Is there anyone who feels uncomfortable still with these 2 questions? These 2 are kind of easy variants that you can do and manage. Okay, Kaushik has a question. On previous code, for some nodes, we have one child, then we push a node and null with null point jumble over code. Okay, let's see, Kaushik. So you have a valid point. So Kaushik has a doubt. What if any level does not have full nodes filled there? Will that code still work? So if it is 13, 9, 10, 10, let me take 11, 10, and 12. So let's see, Kaushik, will our code still work? In Q, we are putting 13 and null initially, right? Now, when you take 13 out, you are printing 13, that's it. And 13 is putting its child in the queue, so 9 will go in the queue. That is what 13's job was. 13 prints himself, puts its children, gets away, that's it. Now, next, we'll look at this. Null comes out. When null comes out, you are giving a new line. Now, since queue is not empty, you are putting another null. So your queue looks like this. At the 2 iterations of the loop, you have removed 2 values and taken action accordingly. Now you take 9 out. 9 will be printed here, and 9 after printing himself, it will queue 11 because that is the only child 9 has. So 9 is gone, printed, 11 is kept. Now null comes out. Null will just do a new line here. And null will also put another null because now you see queue is not empty. So when queue is not empty, we put another line. Now you take 11 out. 11 will print himself. 11 will put its children in the queue, and then 12, and 11's job is done. Now you say null comes out. Null puts a new line. Now 3 lines of output has already been produced. This null will put another null. Now 10 comes out. 10 prints himself here and gets removed. 12 comes out, print himself, gets removed. Now null comes out. The moment you take null out, null will give a new line, and null will see the queue has become empty. Let me not put another null. Kaushik, this will be the output. Does that clarify your doubt? Yeah, so it will work even if you do not have every level properly filled. So this code should actually work, because these nulls are actually telling whenever the level gets over. Doesn't matter how many nodes each level has. So let's get back to our original tree. Okay, so these 2 are relatively easy problems that you can manage. Let me, along with this, let me also put the rank being 0. Tree problems are there in this contest, so I'm just finding the right slot or right page where the tree problems begin. Elements of yeah. So this level order traversal, level order tree to okay, level order in new line is not there in this. But yeah, let me put this direct link, because here the tree problems begin, and you can height of BST traversal. So this is the page number 7 onwards, tree problems begin. So depending on which problems you want to try. Level wise, one problem that we just discussed, I think it is not there, that each level print in a separate line. Oh yeah, this is the problem. So here, each level you are printing on separate line. Now, these problems are different. They are not BST problems. Here, you are creating a tree from two traversals. So you are given pre-order traversal and given in-order and pre-order traversal. Using these two traversals, you have to construct the tree. So I'll give you template code for that also, so that you right now you do not struggle with creating tree. So there is a template for that. Let me remove pretty print code because it makes code a lot clumsy. Yeah. Make sure at least the tree creation is not your worry right now. You can focus directly on writing the functions and you get familiar with that. Later on, you can worry about how the tree is being constructed and look at the code. So this is creating a generic binary tree. This is not binary search tree. So this will be binary tree code.cpp. Yeah, given two traversal, it can construct the tree for you. So this is pretty print. Let me get rid of this. And this code will be G++. The file name that I had kept was binary tree code. G++ binary tree code. This compiles. So yeah, this is your code to construct tree from two traversals, which are pre-order and in order. So C++. Sorry. Yeah. So if I take any pre-order and in-order traversal, do we have some file? BST. Yeah, let me give you one sample input from this one. So one test case, if this is the input, and this should ideally form the tree. Yeah, so this is the code for construct tree from in order and pre-order. So you can directly use this code for creating the tree, and then you can write your functions. So ideally this creation code also, if you see this G++ basic binary tree, where is the other file? Being zero tree template. G++ being zero tree template. If I compile this code, whatever input we have just given, let me give that input to a.exe. One test case, 7 nodes. So this will also print the tree. This is showing, this is what our tree is. Now you can play around with various inputs. So this is with pretty print, this code. Okay, let's come to the third question. Print vertical order of a binary tree. Now, what is vertical order and how do we go about that? So vertical order traversal simply says your output should be this straight line of every level. So the way levels are measured is root is at 0. This is distance 1 when you go left. This is distance, sorry, axis wise. If you take x-axis wise, this is -1, this is -2. Now when you go right from here, this is 0. When you go left from here, this is -1. So ideally I'll say this is one vertical, this is another vertical line, this third vertical line, and ideally 19 also falls in this range, because from 0 you go here 1, you come back 0, you go here 2. So this is what we are marking is distance from the root, distance from origin. From if you go distance 1, in that range, if you see, this is 1, this is 2. So let me redraw the tree so that we can clearly see. So 13, I'm changing the tree values now. So this is currently you are at origin. When you are going left, you are going to -1. This is, let's say, 9. And now I'm making binary tree, not necessarily binary search tree. From here, let me go to 7. So you are making it -2. From here, let's put 2. So now if you see, this is -1, this is -2, but this will again come back to your origin. Now when you go right from here, 13, 15, and when you come 8, 8 is actually at origin level because this is at distance 1. When you come left, you are coming back 1 distance. So you are coming to origin. When you go to right, this is, let's say, 17. So your vertical traversal simply says, first print this vertical line, whatever is the farthest from root on the left side, print 7, then print 9, then print 13 to 8, then print 15, because that is the only thing at this level, then print 17. So your traversal that we are looking at is 7, 9, 13 to 8, 15, and 17. So question is clear. What is our vertical order traversal? Now the question is, what should be our strategy to do this vertical order traversal? How do we do vertical order traversal of our tree? You guys, any thoughts, any ideas? For vertical order, we can take a map of int, vector of int, and fill the vector based on the distance from the root. That is correct. Yeah, so ideally we can take either iterative approach or recursive approach, like we were talking about previously. Also, there can be 3 approaches. So let's see. Let's go with this map-based approach that will help us track the levels. 17. So what you are suggesting ideally is, you are saying let's start from the root, and this distance from the root is going to update its children. So can I say we are talking about, first we can talk about a recursive approach where we say parent passes level to the child or distance to the child. So 13, when we call, we are saying we are passing it a value that you are at origin directly. So function signature of vertical traversal will look like void vertical traversal BT node. I'm not writing BST node, I'm writing BT node because it can be any tree, not essentially BST. And now we are saying we need a helper because we want to add a parameter, vertical traversal helper. BT node R, and we are saying, let me put it as D, distance from the origin. So what distance we will pass to the root? What is the distance of root from the origin? Yeah, it is 0, so we'll pass 0. Now it is root's responsibility to tell its children what is your distance from the origin. So can you tell me, when we make a left call, we have to pass 2 values, right? So what will those 2 values be? When we make a left call, R will make a call to left, what will it pass as the second value? So Kushal says -1 + 1, but Kushal, that will be -1 and +1 to D. Left will say D -1, because whatever you got from your parent, you have to do -1 from that. And for right call, you have to do arrow left, right, D +1. This is just our thought process. Now let's see the strategy, what our strategy looks like. Root got 0 as initial call. So 13 knows I am at level 0. So why people said we will use map is because in map you can store level number or the distance from origin and the value. So you are saying distance from origin, the value is 13. But at any distance, at a -1 distance, you can have multiple values also. Like if you see at 0 distance, there are 3 values. So here, the map that you are taking, the thing can be map will be having a vector. So ideally, your answer you are storing will be in some sort of map of int, comma vector of int, in case you want to assemble or gather all the information. So this is map where key is distance from origin, and value is nodes at that distance. Okay, so 13 got 0. 13 adds himself to map. In map at 0 key, it is saying let me add myself to the vector. So this vector got one value 13. Now 13 makes a left call, and left call it got d as 0, 0 minus 1. So it is calling 9, and 9 is getting a call with minus 1 as its distance. So what 9 will do, at minus 1 it will add himself to that vector. Now 9 will make a call to 7, and it will pass its level as its distance as minus 2. So at minus 2, 7 will add himself. Now 7 will make a left call, but that is null. There is no left child of 7. We will have a boundary case in our recursion where we will return back immediately when we are going left. We will not do anything. Now that call comes back. It will make a right call that will also return back. It's a boundary case. 7 is done making both the calls. 7 will go back to 9 and say, hey 9, I'm done. Now 9 will make a right call. 9's distance was minus 1. Because it is making a right call, it will say minus 1 plus 1. It will pass 0 and say 2. I'm calling you with 0. Now whenever we are at 2, what will 2 do? 2 will go to the map at key 0, and 2 will append himself to that vector. So 2 is appended here after 13. So at 0, we got 2 values. Now 2 does not have left child, does not have right child. 2 will wind up the recursion call stack, go back to 9. 9 will go back to 13, and 13 will say my left side is done. 13 will make a call to 15. The level distance it will pass is 1. Now 15 says 1 is not there in the map. Let me put 1, and I am there at 1. Now 15 will make a left call to 8. 8 will be called with d as 0. 8 will append itself to. Now 8 will go back to 15. I'm done because I have left child null, right child null. Now 15 makes a right call to 17. 17 has distance 2. 17 will be put here. So eventually, once your map is built, in map you have to print the map starting from the list, because your vertical order traversal said find out the least level or least distance and find out the max distance. So, and this will be a continuous range. So from minus 2 to 1 or to 2, you have to do a loop. For every key, you just have to print their vectors. So that is the approach. Now code wise, you can figure out like how you are going to code this. But this is what the vertical order traversal is. So anybody to whom it is not clear? Kushal? Clear? Perfect. So now you can kind of give it a try. So these problems are also there. We'll go back once and see whether top view is there, vertical order traversal is there. So left view, right view, I'm not sure whether we have here or not. So if you don't find left view and right view here, what you can do is you can search for those problems in Geeks for Geeks or LeetCode. Left view of tree, Geeks for Geeks. So you want to make sure that you are able to do these problems with ease, so that next time if somebody asks you, you do not struggle for these problems. We have a practice link, yes. So we have left view here. Yeah, so yeah, rest all I'll leave up to you to find and solve those problems. So let me go and put this at least left view link over here. Vertical you already have. Okay, Dhruv is asking a question. How do we find overlapping nodes in the tree? So what do you mean, Dhruv, by overlapping? Do you mean like here when we are coming to this? Is it in relation to the vertical order traversal or the previous one? Yeah, Dhruv. If you have mic, can you unmute yourself and speak so that will be more clear to hear your. Like in previous tree, 2 and 8 are overlapping. Yes. So how we are detecting the overlap is through every node is getting its distance from the origin, right? Which parent is passing. That is what our function signature was. So if you look at the function signature that we figured out, that we fixed, was parent is telling D to everyone. So every child gets to know a D. And if map is global, can I say every node can say map of D dot pushback or arrow data. So you are actually appending yourself. Each node is appending itself to the vector, because map is a map of int and vector of int. Now what will happen? Your map is getting formed in such a way that your zero level things, zero distance things are 13, 2, and so 13, 2, and 8 will actually get appended in map at key 0, because in map when you are appending, distance is your key, and all the values will automatically come that way. So overlapping things will always fall in one vector. So Dhruv, is that what your question is? Yeah. Okay, so Shravan has responded something. If any level has size greater than 1, then it is overlapping. Right. So once you get the map, eventually you have entire information in the map. So if you build a map, if somebody tomorrow modifies your question, if somebody says that print the vertical order traversal in such a way that output should be in this order. So output should be 8 should be first printed, then 2, then 13. Actually, you are coming from this side. Vertical order traversal, but in reverse way. If your map is built, can you print that easily, reverse side? Because all you have to do is at any level, you have to print it, the vector reverse. So Dhruv, is your question answered? Will this help if we create a map of pair distance? Yeah, that is something, Dhruv, that will help you in the next question when we talk about the top view. In vertical order traversal, you can easily manage with this. Yeah, but you will need what you are talking about. You will need that in the top view. That is the next question we are going to talk about. But for this, why unnecessarily take a map of pair? Because level is immaterial right now to us. In this problem, if we just build a map and at every distance we are putting the values in the vector, we can print it either this way or this way. Anything we will take care of from this. Okay, so this is the vertical order traversal of this tree, and where we have seen, like, we took help of a map and we solved the problem. Now there is one more question which says do top view of the tree. Now top view of the tree means you are seeing the tree from above. If you are seeing the tree from above, 13 will hide 2 and 8. You will not be able to see 2 and 8 if you are seeing tree from top. Then the answer that you have to print is, you'll be able to see 7 because 7 is not being hidden by any other node above it. 7, 9, 13, 15, 17. That should be the output. 2 and 8 will get hidden. If 17 had a left child, let's say 11, even that will be hidden. So this problem is called print top view of the tree. That means at every distance from the origin, you have to print only that value that is the first value at that level. So this problem is, I will say, medium level problem, not an easy level. Like previous three we discussed were quite easy if you are comfortable with recursion and STL. In this problem, you have to combine two things. You have to see the distance as well as you have to know the level of a node, which level you are operating at. Because a node at lesser level will hide the node at higher level, even if their distance is same. Right? Like distance 0, 13 gets a preference. Reason 13 is getting a preference is because its level is lesser than 2's level of 8. Same way, 9 will get preference because at this level, at level 1, this is the first node we are seeing at distance -1. So for that, ideally, if you are taking this approach for top view of the tree, you will have both the things passed, level as well as distance. And this is something I'll let you figure out what will be your logic. But when you are calling left child, you will pass d minus 1, but level will always be l plus 1. And right side will be passed with d plus 1, your level is still l plus 1. And this will be top view of the tree. And remaining thing you need to figure out. But strategy wise, you saw we are going to every distance and we are printing only the least level thing. And that is what we are calling as top view of the tree. And this is a, I will say like this is a must try problem that you should do. And this, if you find in Geeks for Geeks, you should solve there also. In fact, you should solve here also. So this is, yeah, Shawan. So I'll say like try this problem, and this will enable you to kind of clarify a lot of things about your recursive thinking as well as your STM. Right. So this is about top view. So top view wise, our conclusion we are saying is at every level, sorry, at every distance, you are printing the first node that you see at that level. And this problem has another variant called bottom view of the tree. What will change if you go with bottom view? If you are seeing the tree from bottom, then 8 will be printed, 2 and 13 will be hidden. Okay, so Zaki has a question. Wait. Sir, what if we check whether element exists before inserting? Then we will not need to use extra parameter. Yes, Zaki, you can try. If you have any other approach that you feel like it may work, I will say go give it a try. So we are not saying this is the only solution, right? Yeah, in bottom view, you can use only map with intent. That answer is correct. Yes, Rajesh, you can do that. So all these 5 problems, I will say, try any approach that comes to your mind. Don't think like there is only one solution. Approach wise, we are saying that all you need is when you are reaching any level, ideally, some people say I can use level order traversal also to solve the problem. Go give it a try. We'll spend another class in discussing their solutions, or I can share the editorials and solutions with you. But once you should give it a try yourself so that you have struggled, you have reached to your conclusions, and then you can see what are the other solutions possible. Yeah. So Kushal, coming back to you, do you feel comfortable in top view, bottom view, vertical order? Thought process wise, you are clear? Yeah. Okay. So this is what we had for today. So I think you can get started. So you have, every one of you have access to this note. I'm just pasting it once again in the chat window. People who joined late, this note you will be able to access, and problems links are also there in this note. So yeah, so this will help you get started with these problems. Now we can do similar sessions. I do not want to host these sessions every day, but we can have a plan like whenever people are done. You should have some time to do these problems, but we can have more of these sessions since college is not there these days. So thanks to coronavirus. So and these online sessions do not require any traveling also. So we can achieve a lot of things in this 1.5 hour. So future topics that you would want these sessions to be in. If you have any thoughts in your mind, let's do that quick analysis here. You can type in the chat window. If there are enough votes for any topic, I can take up the topic, and but I would plan that session after 2-3 days only, not immediately tomorrow. So any topics that are there in your mind? Okay, Vishal says graph. You guys feel free to cast your votes so that we can have a interview questions on DP. Okay. Graph, one more vote. So graph has 2 votes. Okay, graph has 3. Tarish says graph. DP graph. Okay. Okay. So DP and graph are what I see is most voted. Any other? Okay. Divide and conquer. Shaman says. Will be 1. Graph is another one. 5. Backtracking, Rajesh says backtracking. Okay. Greedy one. Graph, another vote. Okay, backtracking, another vote. Okay, backtracking problems. Geometry related. Geometry, I guess, is from interview perspective, it is not that important, but yeah, it is from competitive programming, it is. So geometry. Divide and conquer, another vote. Shravani, sorry. Geometry 2. Game questions. Game theory from Kushal. Kavya, hash map. We have spent enough time on hash map. And if you have not solved mentor pick problems, I'll suggest you to do that. Because in map, I think in map category, we had put at least 7 to 8 problems. So I don't know if you have seen and paid attention to them. Kavya, have you done those problems, map related problems on mentor pick? All problems. Then what is the question about hash map? If you can clarify, I can see like what is it that we are looking forward to. But let's discuss Kavya offline. I just want to understand that whichever area you are struggling with, at least I understand that well is hash map. Yeah, hash map is same. Ideally, okay, the topic wise, if I understand, you are asking more detail on hashing. Is that correct? Yeah, map is one way of achieving hashing because ideally we don't have to write our hash function. Map has built-in way of doing hashing for us. Okay, so what I see is, yeah, graph has more votes. So we'll begin with that. DP, I think 2 more votes I missed in between. So let's take next few sessions. I think one we will do on tree if there are any questions after trying these problems. If we can sort that out on WhatsApp group, that will be better. Then we will get more time. We can spend next class on graph. Right. So I'll update in the group when we can host the next class. I hope this session was useful. At least you got to learn, and this is more. I mean, this is a good experience for you guys. Okay. So perfect. Thank you guys for staying awake till late. Yeah. So do work on these 3 problems, and then we will plan our next session on that.
Thank you, sir.
Okay, most welcome, man.